Okay, let's get started here. Number 54 is next. From the equilibrium concentrations given, calculate the Ka for each weak acid and the Kb for each weak base. Here's the first one is ammonia, and the reaction from ammonia is going to be NH3 plus H2O goes to form NH4 plus OH minus. So the Ka here is going to be the concentration of NH4 times the concentration of OH minus divided by the concentration of NH3. And you'll notice in the book it shows this as a liquid. This is aqueous, and this is aqueous, and this is aqueous, meaning these are the three concentrations you need. You don't have a concentration for the concentration of water. So this is going to equal, for the concentration of ammonia, it's 3.1 times 10 to the minus 3. For the concentration of hydroxide ion, it's going to be 3.1 times 10 to the minus 3. And for the concentration of ammonia, it's 0.533. And so then you just do the math here, and you get 1.8 times 10 to the minus 5. The next one is HNO2, I believe it is, plus water, goes to form H3O plus NO2 minus. And the concentrations they give you here, now in this formula up here, if we write this down, it's going to be H3O plus NO2 minus divided by HNO2. So in this case, the HNO2 is 1.07. The H3O plus is 0.011. And the NO2 minus is 0.0438. If you do the math here, you get 4.5 times 10 to the minus 4. And that's the Ka for this. So let me skip down to, now D is interesting because what it's showing here is the reaction. For the last one, let's do D. And D is a situation where you have NH4 plus H2O goes to form H3O plus NH3. Now what we're doing here is it's a situation where this is acting as an acid, whereas up here, it's actually the reverse of this reaction in this regard. And so now we have a Ka, which is going to be H3O times NH3 divided by NH4. If we put that in here, NH3 is 7.5 times 10 to the minus 6. H3O is 7, and that's also 7.5 times 10 to the minus 6, so that's squared divided by 0.1. And the answer on this one is 5.6 times 10 to the minus 10. So that's number 54. 60, I actually sent 60A out to you already. 60 is a calculation going, instead of being given the concentrations and working the Ka, you have to look up the Ka in the back of the book and come up with the concentrations. And one of the things that's true about these is when you do that, you can ignore the very low concentration of the product's effect on the concentration of the reactant, which was part of what we had to show. So here we already did A, which was 0.0092 molar HClO, which they tell you is a weak acid. And I believe the answer I sent out was 1.8 times 10 to the minus 5 molar for both H3O plus and for ClO minus. B is 0.0784. So B here is 0.0784 molar C6H5NH2. C6H5NH2. Now this, just when I just look at it, my sense is that this is going to accept a proton, so that this is a base, and indeed it tells you that this is a weak base. So what this tells you is when you write the ionization equation here, so when it's added to water, a hydrogen is going to go from water to form C6H5NH3 plus OH minus. And so the Ka, or Kb in this case, is going to be OH concentration times the concentration of C6H5NH3 plus divided by the C6H5NH2. Now, if you look up this in the back of the book in Appendix H, well, these are all weak acids. So Appendix I is actually the weak bases. And you have to find the right one in here. And I think it's the fourth one down in the table. It's the one that is called phenylamine or alanine. And the Kb for that is 4.3 times 10 to the minus 10. Now, as I explained previously, in these situations, you know, if you subtract whatever the result is here from this number, it is so small an effect that it can be ignored. And so if we give myself a little more room here, we can actually disregard the impact of a decrease in this. So that, in other words, if we put x, and then 0.0784 minus x, and you're more than welcome to put this in here, but it simplifies the calculation if you just say that this x squared is equal to 4.3 times 10 to the minus 10. And if you do the math on this, x is going to equal 2.07 times 10 to the minus 5. Now, if you subtract that from this number, it has virtually no effect on this number, okay? So you really don't have to worry about that. So this is going to equal the the hydrogen or the OH ion concentration, and it's also going to equal the concentration for C6H5NH3 plus. Now the concentration of this is not going to change appreciably. Let's do another one. Let's go with an acid again, HCN. I mean, any of these is okay, but I mean, they're all basically done the same way. So let's look at C, which is HCN. And we have a concentration of 0.081 molar HCN. This breaks down, HCN reacts with water to form H3O plus Cn minus. Now if we go to table H and look at cyanide or hydrogen cyanide, you find that the Ka for hydrogen cyanide or cyanic acid, no, that's not cyanic acid, I'm sorry. Let's see if I can find it here. It's 4.9 times 10 to the minus 10. So the Ka here is equal to 4.9 times 10 to the minus 10. And since I've neglected this in the last two, I'm not going to even put it in here. I'm just going to say that this is equal to H plus H3O plus, plus Cn minus. And if we put an x for each of these, then that means x squared is going to equal 4.9 times 10 to the minus 10. The square root of 49 is 7. 7.0 times 10 to the minus 5. And that's going to equal the concentration of H3O plus, and it's also going to equal the concentration of the cyanide ion. Actually, I made a mistake in both of these. What you put in here is the value for this number. And so this is not correct. I'm sorry that I made this mistake. I hope it doesn't mess you up. So you have to first, before you take the square root, you have to first multiply this number here by this number here. So if we take 4.3 times 10 to the minus 10 and multiply it first by 0.784. So you can't disregard this number, you just disregard the effect of x on this number. And I'm sorry that I got that confused. So if you multiply that and then take the square root, the answer here is actually 5.8 times 10 to the minus 5. Similarly, you need to multiply this number by the original concentration here, 0.081, in order to do this. So if you take 4.9 times 10 to the minus 10, multiply that by 0.081, then take the square root of that, you get, instead of 7, you get 6.3 times 10 to the minus 5. So let me correct it, do one more where I do it right the first time. So let's take a look at D, which is a constant 0.11 of CH3 to the third N, CH3, and that multiplied 3 times to the N. And it tells you that this is a weak base, which means that you have CH3N plus H2O goes to form CH3NH plus OH minus. And the Kb for this, if you look at the table I back here, the Kb for this is going to be, it is the bottom one, triethylamine, 6.3 times 10 to the minus 5. So the Kb is 6.3 times 10 to the minus 5. And what I should say there is that's going to equal CH3, 3NH plus and OH minus divided by CH3N. And here is 0.11, and this is X, and this is X. So if you multiply this, you get 6.3 times 10 to the minus 4, or 5, excuse me, times 0.11 is equal to X squared. So hopefully that straightens out the mistake on the last two that I made. If it doesn't, you can write me a note asking me to explain it again, and I will. And so if you do the math here, you get 2.63 times 10 to the minus 3 for the concentration of both OH minus and of the ionized form of trimethylamine. That's the concentration of both of these. Okay, the last problem is 62. Let's take a look at 62. And 62 says that vinegar is 5% by mass. Now, hopefully you remember what that means. What it's telling you is that it's 5 grams of vinegar per 100 grams of water. It also tells you that the density of vinegar is 1.0006 grams per cubic centimeter. So it's asking you, what is the pH? Let's assume that we have 1 liter of vinegar. If you use the density that you have 1 liter of vinegar, then that means you have 1,007 grams of vinegar. Now, this is 5%. So 5% of this, so you have that much mass of vinegar. And this 1,007 grams is 5%, which means you multiply by 0.05 to find the mass of vinegar, the actual acetic acid, which is 50.35 grams of pure acetic acid, and the rest is water. Now 50.35 grams, and the gram molecular weight of vinegar is 60 of acetic acid is 60.053 grams per mole. So you end up with 0.838 moles. So this ends up being a 1 liter, remember it's moles per liter, 1 liter is actually ends up being 0.838 molar acetic acid. Now from the back of the book, the Ka for acetic acid is 1.8 times 10 to the minus 5. And that is going to equal the acetate ion times the hydrogen ion divided by the undissolved acetic acid ion. So if we put this in our ice equation, we know that we have x of this and x of this, and 0.838 minus x of this. And x is going to be small in comparison, so we can eliminate the x here. So x squared is going to equal 1.8 times 10 to the minus 5 times 0.838. So that x is going to equal 3.88 times 10 to the minus 3, which is going to equal the hydrogen ion concentration. So if we use our previous formula that the pH is the negative log base 10 of the hydrogen ion concentration, if we put this number in and do the math, the pH is going to equal 2.41.